Alright, in this video we'll be introducing a new way of drawing carbohydrates and monosaccharides known as a Fischer projection. And in a Fischer projection, we use vertical lines to represent bonds that point away from the viewer, and horizontal lines that represent bonds that point towards the viewer. And so if we draw out the simple sugar glyceraldehyde, and we'll use wedge and dash bonds to represent these different bonds. Oh, nope. This should just be H. So this is one enantiomer of glyceraldehyde, and this would be the other enantiomer So we're drawing it a little different from other structures in that we've sort of taken the tetrahedral structure around this carbon and we've rotated it such that two of these groups, this hydroxyl group and this hydrogen, point towards us, so that the other two groups, this aldehyde and this CH2OH group, point away from us. And once we rotate it in such a fashion, then it becomes relatively easy to draw the Fischer projection. Which doesn't use wedge and dash bonds, but just uses vertical and horizontal lines. And so these horizontal lines point towards the viewer, and these vertical lines point away from the viewer. So these diagrams show essentially the same thing as these other diagrams with the wedge and dash bonds in order to show the groups that point towards us and the groups that point away from us. Another thing that we can do with Fischer projections is we can easily identify whether these molecules fit into what we call D or L categories. And what we do here is we look at the hydroxyl group on the last chiral carbon, which in this case would be here or here. Or if we look at our wedge and dash bonds, it would be here and here. So again, we start at the carbon with the aldehyde or the ketone. So we place that up at the top and we move down the molecule till we get to the last chiral carbon. This last carbon is not chiral because it has two of these hydrogen atoms on it. And so that means it's not chiral because it has two of the same group. So we have to stop at the last chiral carbon, which is the last carbon that has four different groups attached. In this case, the OH, this CH2OH, this aldehyde, and this hydrogen all make up the four different groups. But anyway, we classify these as D or L based on the position of this last chiral hydroxyl group. If it points towards the right, then it's D. If it points towards the left, then it's L. So this is D glyceraldehyde. This would be L glyceraldehyde. And then with the Fischer projections, again, it would be D and L. And the reason that this becomes important is because almost all sugars are found in nature. Almost all naturally occurring sugars will be D sugars, which means that if we took all the glyceraldehyde molecules on the planet and we sorted them into D and L, almost all of those would be D glyceraldehyde. The L glyceraldehyde exists, but it's almost all produced artificially in laboratories rather than by living organisms. And so when we look at glyceraldehyde, we only have this one chiral carbon. We'll mark that with an asterisk. And because we only have one chiral carbon, there are only two possible enantiomers, the D-glyceraldehyde and the L-glyceraldehyde. But as we move up to larger sugars, such as glucose, then we get more possible stereoisomers. And so we'll use a Fischer projection to represent glucose and demonstrate what I mean. So, again, glucose And so I'm taking my time a little drawing this glucose to make sure I get the hydroxyl groups in the right positions. Because glucose has a specific order of these hydroxyl groups. Oh, nope. And so, again, using our Fischer projection to identify D and L, we come down here to the last chiral carbon. We look at its hydroxyl group. This one points towards the right, so this would be D, glucose. This one on the other side points towards the left, so this is L, glucose. And now glucose has more than one chiral carbon. In fact, it has 1, 2, 3, 4 chiral carbons. And so that 2 to the 4th equals 16 possible stereoisomers. And I've shown 2 of them here, D-glucose and L-glucose. These are enantiomers of each other because they have all of their chiral carbons inverted. We've flipped the position of every single chiral carbon. And so we call them enantiomers. That it's just like a left-handed and a right-handed version of the molecule. But if we change only one of these chiral carbons, then it's not called an enantiomer, it's called an epimer. And an example of an epimer of glucose is another sugar called galactose. And so we'll draw galactose. And galactose has a hydroxyl here, 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 here. Our CH2OH will fill in our hydrogens. And again, our last chiral hydroxyl group points to the right, and so this is D-galactose. But we flipped one of these groups relative to glucose. For example, here and here are different, the D-glucose and the D-galactose. We flipped the orientation at this third position. And in fact, we should introduce the numbering system for these. This first carbon up at the top with the aldehyde would be carbon 1, 2, 3, 4, 5, and 6. And so again, with the galactose 1, 2, 3, 4, 5, and 6. And so galactose is what we call a C4 epimer of glucose. Because it's the epimer of glucose. We've only changed one of these chiral carbons, and we've changed that at the fourth carbon, so that's C4. It's the C4 epimer. That there are other sugars that are produced by taking glucose and flipping the position of one of these. That we'll make some room here real quick. We'll redraw our galactose. So again, D-galactose. If we were to change, not at this fourth position of glucose, but if we flipped the first position of glucose, or the C2 position, then we would get D-mannose, which is another sugar found in biological systems. And again, these are D-galactose and D-mannose because this last chiral hydroxyl group points to the right. If we were to line up all of the hydroxyl groups on the same side, then it would be D-allose. And again, it's D because the last chiral hydroxyl group points to the right. And these are just 1, 2, 3, 4 of the 16 different combinations that are possible with this basic formula here for the D-glucose. We can flip any one of these chiral carbons and arrive at a different sugar. These are all different epimers of glucose. So it's important to use these Fisher projections in order to help keep track of the positions of all the hydroxyl groups, whether they're on the left or the right, because that will define the different sugars that we have. And so because different sugars will have different biological activities, that it's important to specify what is what, and that the only thing that changes, the only difference between glucose and galactose, for example, is the orientation of this C4 position. The only difference between glucose and mannose is the orientation at the C2 position. The only difference between glucose and allose is the orientation at this C3 position. And so just changing the orientation of one position leads to very different sugars they all have similar physical properties, but they have very different biological properties. That it requires different enzymes to digest glucose than it does galactose or mannose or allose. And so some of these sugars just aren't found in nature because living systems don't produce them very much. Other sugars, they aren't digested very easily because we don't have the right enzymes to digest them. And again, it's all the keeping track of what sugar is which can be done using these Fisher projections.